Hello and welcome back. My name is Liam and this is Deep Space Intelligence, the channel where we take the biggest questions about the cosmos and follow them wherever the evidence leads. If you're joining us for the first time, we're glad you are here. This is a place built on curiosity, on careful research, and on a genuine love for the science that keeps pushing the edges of what we understand about the universe we live in. Today, we're going somewhere deeply personal. Not to a distant nebula, not to a black hole billions of light years away, but somewhere much closer and in its own way, just as strange. We are going to talk about you, about the human body, about what happens second by second and minute by minute, the moment a person crosses the invisible boundary between the world we were built for and the alien environment of space. Think about that for a moment. You've been shaped by roughly 3.7 billion years of biological evolution. Every system in your body, your heart, your bones, your eyes, your nervous system, your immune defenses, every single one of them evolved under one constant, relentless, unavoidable force: gravity. From the very first single-celled organisms that clung to the floors of ancient oceans, to the fish that crawled onto land, to the upright primates that became us, gravity has never once let go. It has been the invisible architect of everything you are. And then, one day, in a matter of minutes, it vanishes. What happens next is not just uncomfortable. It is one of the most dramatic physiological transformations a living human being can experience. It is a cascade of changes, some of them visible within seconds, others unfolding quietly over weeks and months, rewriting the biology of the person experiencing them in ways that researchers are still working to fully understand. And the story of how we have come to know what we know is itself remarkable, pieced together from decades of astronaut medical records, painstaking laboratory experiments, and landmark studies like NASA's famous twin study, which gave scientists their most detailed portrait yet of what space does to a human being. So today, we are going to walk through it together. Second by second, system by system, we are going to follow a human body as it enters space, and begins the extraordinary process of trying to adapt to a world it was never designed for. By the end of this, you will understand your own body in a new way, and you will understand space travel and the genuine challenges it poses with a clarity that I think will stay with you. Let us begin. The moment of launch is not a gentle experience. When a rocket like the Space Launch System or a Soyuz ignites its engines and lifts away from the ground, the forces acting on the human body inside the capsule are extraordinary. In the first seconds of ascent, astronauts typically experience acceleration forces of roughly 2 to 3 times the force of normal gravity, what engineers call 2 to 3 Gs. During the most demanding phases of launch, particularly as the rocket accelerates through the lower, denser layers of the atmosphere, those forces can briefly spike higher. The chest compresses, breathing becomes laboured, like trying to inhale against a heavy weight pressing from all sides. Vision can tunnel. The face distorts under the load. Blood is pushed down and away from the head, and the cardiovascular system used to fighting gravity in one direction at a steady rate is suddenly fighting it at a multiplied, punishing rate. This phase of the journey, from ignition to orbital insertion, typically lasts around 8 to 9 minutes for a Falcon 9 carrying a Crew Dragon capsule. For those 8 to 9 minutes, the human body is under siege. The diaphragm fights to move air, the heart races. Every muscle tenses involuntarily. The noise inside the capsule is described by astronauts as almost incomprehensible, a deep, bone-vibrating thunder that you feel as much as you hear, and then, in a transition that many astronauts describe as one of the most surreal moments of their lives, the main engines cut off. MECO, main engine cut off. And in that instant, everything changes. The crushing weight that has been pressing down on every cell in the body simply disappears. The noise drops, the vibration stops, and the human body, which has been adapting to gravitational forces for every moment of its existence, encounters something it has absolutely no evolutionary preparation for: weightlessness. To understand what happens in the first seconds of weightlessness, you need to understand something fundamental about how the body manages itself under normal conditions on Earth. Roughly 60% of your body weight is water, held in various compartments throughout your tissues, your blood vessels, your lymphatic system. Gravity is constantly pulling all of this downward. Your cardiovascular system is exquisitely tuned to compensate for this, using pressure gradients and a network of valves and muscle walls to push blood upward against gravity's pull. ensuring your brain gets a constant, adequate supply. The moment weightlessness begins, that equation collapses. Without the downward pull, there is no longer a hydrostatic pressure gradient running from head to foot. The blood and the fluids that had been pooled in the lower extremities, in the legs, in the abdomen, in the pelvis, begin to redistribute. They follow the new physics, and the new physics says, nowhere in particular. The fluids spread, but the net effect in those first minutes is a significant upward shift, a wave of fluid migrating into the chest and toward the head. Studies and measurements from astronauts in low Earth orbit have documented that this cephalad fluid shift, as researchers call it, moves approximately 2 litres of fluid upward within the first 24 to 48 hours. 2 litres. That is the equivalent of a large bottle of water redistributing itself from your lower body to your upper body. The effects are immediate and visible. The face swells. Astronaut photographs taken within the first few hours of orbital insertion show a distinctive puffiness, a fullness in the cheeks and forehead that was not there before launch. The nasal passages become congested, not because of any infection, but because the tissues of the sinuses are being engorged with fluid that normally drains downward with the help of gravity. Astronauts frequently describe the first days in space as feeling like the worst head cold they have ever had. Pressure behind the eyes, a stuffy nose, a muffled quality to sounds. And at the same time, the legs begin to thin. As fluid leaves the lower extremities, the calves and thighs become noticeably narrower within days. This phenomenon has a nickname in astronaut culture: puffy face, bird legs. It is not dangerous in itself, but it is deeply strange to experience, a physical reminder that the body is not where it belongs. While the fluid shift is producing these outward changes, something equally significant is happening within the cardiovascular system itself. The heart, accustomed to working hard to push blood upward against gravity, suddenly has a very different workload. With fluid pressing into the thoracic cavity and toward the heart from below, the venous return to the heart actually increases in those first moments. Cardiac output goes up. The stroke volume, the amount of blood pumped per heartbeat, increases by somewhere between 35 and 46% in the immediate transition to microgravity, according to data from cardiovascular studies on ISS astronauts. Cardiac output itself rises by 18 to 41% in the initial phase. The body interprets this sudden excess of fluid returning to the heart as a problem. It reads the elevated pressure as a signal that there is too much fluid in circulation, and so it does what it is designed to do when it senses fluid overload. It begins to eliminate the excess. The kidneys increase their output. The body actually suppresses the production of certain hormones, including antidiuretic hormone and aldosterone, the very hormones that normally tell the kidneys to conserve water. Fluid is excreted. Total blood volume drops. Researchers have documented a plasma volume reduction of roughly 10 to 15% in the first days of spaceflight. The body essentially mistakes the redistribution of its own fluids for an excess, and begins dehydrating itself in response. This creates a paradox that space medicine specialists find both fascinating and concerning. At the same time that fluid is pressing into the head and causing congestion and facial puffiness, the overall blood volume is declining. The astronaut feels simultaneously congested and dehydrated. Headaches are extremely common in those first hours. NASA has documented that headache is among the most frequently reported symptoms during the early adaptation phase, and it makes physiological sense given what is happening inside the skull, where elevated fluid pressure is pressing on blood vessels and sensitive tissues. And speaking of the skull, the fluid shift carries implications that go far beyond a stuffy nose or a puffy face. As fluid presses upward into the cranial cavity, the pressure inside the skull, what clinicians call intracranial pressure, is believed to rise. This is the suspected mechanism behind one of the most alarming and most actively studied conditions in space medicine today, a condition known as spaceflight-associated neuroocular syndrome, or as ANS. NASA itself has listed SANS as its leading spaceflight-related health risk. Here is what happens. The eye is not a self-contained bubble. It is connected through the optic nerve to the brain, and the space surrounding the optic nerve is in communication with the cerebrospinal fluid that bathes the brain. When intracranial pressure rises, that elevated pressure can transmit along the optic nerve sheath, pressing against the back of the eye, flattening the globe itself, and causing swelling of the optic disc, the point where the optic nerve meets the retina. Astronauts on long-duration missions have returned to Earth with measurable flattening of the posterior globe, thickening of the optic disc, tissue changes visible on detailed imaging, and, most critically, shifts in their visual acuity. A post-flight survey of approximately 300 astronauts found that 23% of short-duration shuttle pilots reported some decline in near-visual acuity, and that figure rose to 48% among astronauts who spent long-duration tours on the International Space Station. Some of these visual changes have been documented as persistent, lasting months or even years after the astronaut returns to Earth. NASA has confirmed that at least 15 long-duration male astronauts, most between the ages of 45 and 55, experienced confirmed visual and anatomical changes during or after long-duration flights. The exact mechanism is not yet fully understood. Researchers debate the precise role of intracranial pressure, of venous drainage patterns, of cerebrospinal fluid dynamics around the optic nerve. What is clear is that something about long-duration weightlessness and the fluid environment it creates is capable of physically reshaping the human eye. The condition currently has no guaranteed treatment or prevention. It is an open and urgent question in space medicine. Now let us go back to those first seconds and minutes after MECO, because while the fluid system is beginning its dramatic redistribution, another system is simultaneously going into crisis, the vestibular system. Your vestibular system is the machinery of balance and spatial orientation housed deep in your inner ear. It consists of two main components, the semicircular canals, which detect rotational movement, and the otolith organs, tiny structures called the utricle and the saccule, which detect linear acceleration and crucially the direction of gravity. Small crystals of calcium carbonate called otoliths rest on a gel membrane above sensory hair cells. On Earth, gravity constantly pulls these crystals downward, providing the brain with a continuous, reliable reference signal. This is which way is down. This is how fast you're moving. This is how your head is oriented relative to the ground. In weightlessness, the crystals no longer settle in any direction. The gravitational reference point that your vestibular system has relied upon every moment of your life simply ceases to exist. The otolith organs, unmoored from their lifelong anchor, begin sending signals the brain does not know how to interpret. Meanwhile, the eyes are looking at a stable cabin interior that offers no natural horizon and no consistent up or down. The proprioceptive system, the network of pressure and stretch receptors throughout the muscles and joints, is reporting a complete absence of the weight-bearing forces it normally registers. The brain receives contradictory signals from every direction. Vision says, we're in a stable room. Vestibular system says, nothing or something that makes no sense. Proprioception says, we are falling, or we are weightless, or we are upside down. The brain cannot resolve this conflict, and the result for a very large proportion of astronauts is a reaction that evolution designed for a very different situation: nausea, disorientation, and vomiting. This is Space Adaptation Syndrome, or SAS. It affects approximately 60 to 70% of all astronauts during the early days of a mission. It was effectively unknown in the first crewed missions, which took place in capsules so cramped that there was essentially no room to move, meaning the vestibular system was rarely challenged by changes in body orientation. It became significantly more common as spacecraft grew larger and astronauts could float freely through multiple modules. The first widely documented case is believed to be Soviet cosmonaut German Titov on Vostok 2 in August 1961, who reported dizziness and nausea, but early cases were sometimes concealed because admitting to incapacitation was not something astronauts were eager to do. Today we know it is extremely common, deeply disorienting and largely unavoidable. The symptoms can be severe: nausea, cold sweats, vomiting, a profound sense of disorientation that makes it difficult to focus on tasks. Some astronauts have described losing their sense of which way they are pointing entirely, of looking at the floor and not being able to determine whether it is beneath them or above them. Frank Borman, commander of Apollo 8, the first crewed mission to orbit the Moon, was ill with what was initially reported as a gastrointestinal bug, but is now understood to have been space motion sickness in a high-intensity form. Astronaut Rusty Schweickart on Apollo 9 experienced it severely enough that a planned spacewalk had to be modified. In the modern era, NASA schedules no extravehicular activities for at least the first 72 hours after arrival in orbit, specifically to give astronauts time to move through the worst of the adaptation process. The body does adapt. Within 2 to 3 days for most astronauts, the brain begins constructing a new model of spatial orientation, one that relies more heavily on vision and less on the otolith organs. The nausea subsides, the dizziness fades. The astronaut begins to navigate their new environment with increasing confidence, but this adaptation is to weightlessness specifically. When they return to Earth, the entire process reverses, and many returning astronauts stagger as they try to walk, their brains now accustomed to a world without gravity, suddenly unable to make sense of the gravitational pull they once took entirely for granted. While the vestibular system is fighting its disorienting battle in those first days, and while the cardiovascular system is redistributing its fluids, the spine is beginning a transformation that is both remarkable and, in the long run, potentially dangerous. The human spine is an extraordinary structure, 24 mobile vertebrae stacked in a column, each pair separated by an intervertebral disc, a tough outer ring of cartilage surrounding a gel-like nucleus that acts as a shock absorber. Under normal gravity, the discs are constantly under compression. The weight of the upper body, the tension in the muscles, the simple downward force of gravity are always pressing the vertebrae together and squeezing the discs. Over the course of a normal day on Earth, you actually lose a small amount of height as your discs compress slightly under this load. This is why you are measurably shorter in the evening than when you wake up in the morning, by somewhere between 1 and 2 centimeters. In microgravity, the compressive load on the spine disappears, and the discs, no longer squeezed, begin to absorb fluid and expand to a more natural unloaded state. As each of the 24 discs swells slightly, the cumulative effect along the entire length of the spinal column is significant. Measurements from ISS missions have documented an average spinal elongation of approximately 4 to 5 centimeters during long-duration spaceflight. For a 6-foot astronaut, this can represent nearly 2 inches of added height. NASA engineers actually account for this when designing spacesuits, incorporating extra length in the torso section to accommodate an astronaut who will be measurably taller inside the station than they were at launch. This spinal expansion sounds almost appealing, a kind of cosmic chiropractic treatment. The reality is considerably less comfortable. As the natural curvature of the spine, its characteristic S shape, straightens out under the unloaded conditions of microgravity, the muscles and ligaments surrounding the spine, which evolved to work in the context of that curvature, find themselves in a new and unfamiliar configuration. The paraspinal muscles, the deep muscles that run alongside the vertebral column and are critical for stability and controlled movement, begin to atrophy relatively quickly. Data from MRI imaging of ISS crew members before and after 6-month missions has shown measurable reductions in the cross-sectional area of the lumbar paraspinal muscles. Back pain is one of the most commonly reported medical complaints during spaceflight. A study examining the problem found that space adaptation back pain, or SABP, occurs in approximately 52% of space travelers during the first 2 to 5 days of flight, and there is a serious downstream consequence. NASA crew members have been documented to have a 4.3 times higher risk of herniated intervertebral discs compared with the general population and military aviator populations. The highest risk occurs during the first year after a mission. The discs that expanded in the absence of gravitational load, now swollen with fluid and altered in their internal biomechanics, are poorly prepared to handle the abrupt recompression that comes with returning to Earth. Astronauts have come home from the International Space Station and then herniated spinal discs months later during seemingly ordinary activities, the biological legacy of a spine that was stretched, unloaded, restructured, and then suddenly asked to carry full gravitational load again. This is, incidentally, a good moment to note something important. Everything we are discussing today is drawn from documented research, peer-reviewed studies, NASA medical data, and the testimony of astronauts and space medicine specialists. Science is a process, and our understanding of what space does to the human body is constantly being refined. I always encourage you to look into these topics yourself, to read the primary sources where you can, and to approach everything, including what you hear on this channel, with thoughtful skepticism. The goal here is never to simply tell you what to think, but to give you a foundation for your own informed exploration. Now, while the spine is expanding and the fluids are migrating and the vestibular system is staging its rebellion, something is also beginning to happen to the bones and muscles of the body more broadly. And this is where the long game of spaceflight physiology becomes genuinely alarming. Bone is not static material. It is living tissue, constantly being broken down by cells called osteoclasts and rebuilt by cells called osteoblasts. On Earth, the mechanical stress of bearing weight and moving against gravity is one of the primary signals that tells the body to maintain bone density. Remove that mechanical signal, and the balance between breakdown and rebuilding shifts. The osteoclasts keep working, the osteoblasts slow down, and the result is bone loss at a rate that would be extraordinary in any other context. Measurements from ISS missions have documented bone mineral density losses in astronauts at a rate of approximately 1% per month. 1% per month. To put that in context, a postmenopausal woman on Earth, who faces some of the most significant bone loss seen in normal human aging, typically loses bone at a rate of 1 to 2% per year. An astronaut on a 6-month mission may lose more bone density than that in a single month. After a 3 to 4 month mission, recovery studies suggest it takes approximately 2 to 3 years to fully regain the lost bone density after returning to Earth. After a year in space, recovery is even more uncertain. Some long-duration astronauts have not returned to their pre-flight bone density levels even years after landing. The bones most affected are the weight-bearing bones of the lower skeleton, the femur, the tibia, the pelvis, the lumbar spine. These are precisely the bones that bear the most load on Earth, and therefore receive the strongest mechanical signal to maintain their density. Remove that signal for months, and the signal's absence speaks clearly to the biology. We do not need this bone anymore. The elevated calcium levels that result from bone demineralization add another layer of risk. As calcium floods into the bloodstream from dissolving bone, some of it is excreted by the kidneys. This elevated urinary calcium, combined with the reduction in fluid intake that often accompanies adaptation to weightlessness and the shift in kidney function, significantly increases the risk of kidney stone formation. This is a serious concern in a spacecraft environment where surgical intervention is not an option and kidney stones can be agonizingly painful and potentially life-threatening. The muscular system faces a parallel challenge. Muscles, like bones, are maintained by use. The constant low-level work of standing, walking, balancing, and carrying your own body weight provides a continuous stream of mechanical loading signals that tell the body to maintain muscle mass. In weightlessness, that continuous loading disappears. Moving from one end of the space station to the other requires almost no muscular effort. The legs, which on Earth are in constant use simply keeping you upright, become largely redundant. Without the use it or lose it signal, the muscles begin to atrophy. Researchers have documented significant decreases in muscle mass, strength, and endurance during spaceflight, particularly in the muscles of the lower body and back. Protein synthesis in muscle tissue slows. The ratio of fast-twitch to slow-twitch muscle fibers can shift. In the most basic terms, the muscles shrink because the body concludes it is wasteful to maintain them. This is why astronauts on the International Space Station exercise for approximately 2 hours every day, 6 days a week. The exercise regimen is not optional. It is a medical countermeasure, a deliberate effort to simulate some of the loading signals that gravity normally provides for free. The station carries specialized equipment for this purpose, including an advanced resistive exercise device that allows astronauts to perform exercises equivalent to weightlifting by working against the resistance of a vacuum piston system rather than actual weights. It also carries treadmills and cycle ergometers. This regimen significantly reduces, though it does not eliminate, the muscle and bone losses associated with long-duration spaceflight. Astronauts who exercise more consistently during their missions show less atrophy and less bone loss than those who exercise less. But even with 2 hours of exercise daily, measurable losses accumulate over a 6-month mission. Now we need to talk about something that is arguably even more serious than bones and muscles, something that is invisible, that passes through the hull of the spacecraft and through the walls of the body without being felt. Something that has been identified by researchers as the single greatest obstacle to long-duration deep space exploration beyond Earth orbit. Radiation. On the surface of the Earth, we are protected from the most dangerous forms of space radiation by 2 shields. The first is the magnetosphere, the vast magnetic field generated by Earth's liquid iron core, which deflects charged particles streaming from the Sun and from deep space. The second is the atmosphere, roughly 100 kilometers of air above us that absorbs and scatters high-energy photons and particles before they reach the ground. At the altitude of the International Space Station, roughly 400 kilometers above Earth's surface, the magnetosphere still provides a degree of protection, though astronauts are exposed to significantly higher radiation levels than people on the ground. Measurements from the ISS have documented that astronauts in low Earth orbit receive approximately 0.5 to 1 millisievert of radiation per day, which over the course of a 6-month mission adds up to more than 10 times the annual radiation exposure that people at the Earth's surface experience in a year. But the ISS, for all the challenges it presents, is still within Earth's protective magnetic umbrella. Beyond low Earth orbit, in the deep space environment that lies between the Earth and the Moon, and further toward Mars, that protection largely disappears. 3 primary sources of radiation threaten travellers in deep space. The first is solar particle events, intense bursts of protons and other charged particles thrown into space by solar flares and coronal mass ejections. These events can be sudden and intense, producing radiation levels in deep space that could theoretically be lethal without adequate shielding within a matter of hours. They are partially predictable, because solar activity can be monitored, but only partially. The second source is the Van Allen radiation belts, regions of charged particles trapped in Earth's magnetic field that any spacecraft leaving Earth must pass through. Transit is brief, a matter of hours, but the radiation density in the inner belt is intense, and the cumulative dose received during transit, particularly if the spacecraft passes through at an unfavourable trajectory, is significant. The third, and in many ways the most formidable source, is galactic cosmic radiation. These are not particles from our own sun. They are extraordinarily high-energy particles, protons and the nuclei of heavier elements, accelerated to near-light speed by supernova explosions and other violent astrophysical events in the distant galaxy. They arrive continuously from all directions, a steady isotropic rain of radiation that passes through spacecraft hulls and human tissue alike with remarkable ease. They cannot be stopped by conventional aluminum shielding. In fact, high-energy galactic cosmic rays interacting with shielding material can create secondary radiation showers that in some configurations actually increase the dose. Traditional shielding strategies effective against solar particle events, made from hydrogen-rich materials or water, are more promising against galactic cosmic radiation, but the physics of high-energy particle shielding remain a deeply challenging engineering problem that no current spacecraft has fully solved. What does this radiation do to the human body? At the cellular level, it causes ionization. Passing through tissue, these high-energy particles strip electrons from atoms, creating reactive ions and free radicals that can damage proteins and, most critically, the DNA within cells. Galactic cosmic ray nuclei, particularly the heavier iron and silicon ions that travel at near-light speeds, can produce dense tracks of ionization damage through tissue, breaking both strands of the DNA double helix simultaneously in what is called a double-strand break. These complex clustered DNA lesions are significantly harder for the cell's repair machinery to fix accurately than the more common single-strand breaks caused by, say, an X-ray on Earth. The potential consequences include increased cancer risk over the astronaut's lifetime, possible effects on the central nervous system including cognitive function and memory, cardiovascular effects linked to radiation-induced inflammation of blood vessel walls, and potential cataract formation in the lens of the eye. NASA has documented that radiation exposure during ISS missions is correlated with increased cataract rates in astronauts. Studies in animal models exposed to simulated galactic cosmic radiation have produced worrying results, including measurable cognitive deficits, increased anxiety-like behaviors, and structural changes in brain tissue. Whether these findings translate directly to human astronauts remains a critical and urgent area of research. For context, a hypothetical crewed mission to Mars using current propulsion technology would involve a transit time of roughly 6 to 9 months each way, plus time spent on the surface, for a total mission duration that researchers estimate at somewhere between 18 months and 3 years. The cumulative radiation dose for such a mission would be substantial, estimated in some analyses to approach or exceed the current career limits that NASA sets for its astronauts in terms of lifetime radiation exposure, limits that are themselves based on risk models for cancer incidents. This is not a theoretical problem for the distant future. It is an active constraint on the planning of human deep space exploration right now. It is worth noting, as we do on this channel, that the precise quantification of radiation risk for individual astronauts is an area of genuine scientific complexity and ongoing debate. The models used to estimate cancer and other health risks from space radiation are derived from Earth-based studies of radiation exposure from nuclear accidents, bomb survivors, and radiological treatments. Extrapolating these models to the very different radiation environment of deep space, with its unique mix of particle types and energies, involves significant uncertainties. Researchers across NASA, ESA, and academic institutions continue to refine these models, and some recent work suggests that the risks may be somewhat different from earlier projections in various ways, sometimes higher in certain categories, sometimes lower in others. The science is evolving, and it is always worth checking the most current publications if this is a topic that concerns you. Let us return now to the body adapting in orbit and zoom in on something that happens at a scale smaller than organs or bones or muscles, something that happens at the level of the genome itself. In April 2019, NASA published the comprehensive results of what had become its most ambitious human health study, a project years in the making, involving 10 research teams, cutting-edge genomics technology, and an extraordinary natural experiment made possible by an extraordinary pair of brothers. The NASA twin study compared astronaut Scott Kelly, who spent 340 days aboard the International Space Station from March 2015 to March 2016, with his identical twin brother Mark Kelly, a retired astronaut who remained on Earth during the same period. Because identical twins share the same DNA, any differences observed between them during the study period could reasonably be attributed to their different environments, rather than to inherent biological variation between individuals. It was, in effect, a natural controlled experiment at the most intimate possible scale. The findings, published in the journal Science, were remarkable in their breadth and in some cases stunning in their specificity. Researchers found that spaceflight is associated with oxygen deprivation stress, increased inflammation, and dramatic shifts in how genes are expressed, how the DNA instructs the body's cells to make the proteins that run every cellular process. Thousands of differences in gene expression were documented between Scott in space and Mark on Earth. The immune system genes were particularly affected, with Scott's immune-related gene expression showing a pattern described by one of the lead researchers, Cornell geneticist Christopher Mason, as being almost on high alert, as if the body were straining to interpret and respond to its novel environment. Most of these changes in gene expression returned to pre-flight levels after Scott came home. The body, it appears, has considerable capacity to recover from at least a year in space. Most of the biological alterations observed during the mission were resolved within hours to days of landing, but not all of them. Approximately 7% of the gene expression changes that were documented during the mission had not returned to pre-flight baselines 6 months after Scott returned to Earth. These persistent changes were concentrated in genes related to immune function, DNA repair, and the networks that regulate bone formation and cellular stress responses. The long-term significance of this finding is still being analysed. Perhaps the most unexpected and widely discussed result from the twin study involved a cellular structure found at the tips of chromosomes, called telomeres. Telomeres are, in essence, the protective caps at the ends of DNA strands. Think of the plastic tip at the end of a shoelace, the aglet that prevents the lace from fraying. Telomeres serve a similar function, preventing the chromosomes from degrading or fusing with one another during the process of cell division. They are critically important to cellular health and longevity. One of the established features of normal human aging is that telomeres gradually shorten each time a cell divides. The accumulation of shortened telomeres over a lifetime is associated with cellular aging and the increased risk of various age-related diseases. Given all the stresses of spaceflight, the researchers expected that Scott's telomeres might shorten during his year in space, reflecting the toll of the hostile environment. What they found was the opposite. Scott's telomeres actually grew longer during his time in orbit, an unexpected elongation that surprised the team. Researcher Susan Bailey at Colorado State University, who led the telomere investigation, described the team's reaction as simply surprised. The elongation was real, confirmed by multiple independent assays and genomic testing methods, and then, within 2 days of Scott landing back on Earth, the majority of those elongated telomeres shortened again with unusual rapidity, dropping back toward pre-flight lengths, and in some analyses showing a greater proportion of short telomeres than before the mission. This rapid shortening on return, following the elongation in space, raised its own set of biological questions. The long-term implications, particularly in the context of radiation exposure that may increase the rate of cellular mutation in cells with longer telomeres, remain a subject of active investigation. What drove the telomere elongation? The researchers proposed several possible contributing factors, including reduced caloric intake in space, which is known to affect telomere dynamics on Earth, elevated folate levels detected in Scott's blood during the mission, and possibly the activation of stem cells with longer telomeres being released into the bloodstream in response to the physiological stresses of spaceflight. The truth is that while the observation is robust, the mechanism is not fully understood. It is precisely the kind of finding that demonstrates why extended human spaceflight research is so important and so complex, because space does things to the body that our terrestrial biology did not anticipate, and that our current models do not fully explain. The twin study also documented changes in the microbiome, the vast community of bacteria and other microorganisms that live in the gut and on other body surfaces, and play a crucial role in digestion, immune function, and even mood and cognition. Scott's gut microbial composition shifted measurably during his time in space. The diversity and relative proportions of bacterial species in his intestinal microbiome changing in ways that differed from his brother's relatively stable profile on Earth. The gut microbiome is sensitive to diet, stress, sleep disruption, and a host of other environmental factors, all of which are altered in the spaceflight environment. The precise functional implications of these microbial changes for an astronaut's health and cognitive performance are still being mapped out by researchers. Sleep, too, becomes a different and often inadequate experience in orbit. The International Space Station orbits Earth at approximately 28,000 km per hour, completing one full orbit roughly every 90 minutes. This means the crew experiences 16 sunrises and 16 sunsets in every 24-hour period. The body's circadian rhythm, the internal biological clock that regulates the sleep-wake cycle in response to light and darkness, is designed for a planet where daylight and nighttime each last approximately 12 hours. In the space station environment, the visual cues that normally anchor the circadian system are entirely disrupted. Astronauts work to maintain a regular schedule using the station's artificial lighting systems and careful scheduling, but sleep disturbances are extremely common. Studies have documented that ISS crew members typically sleep significantly less than the recommended 8 hours per night during their missions, often averaging somewhere between 6 and 6.5 hours. Fatigue, reduced cognitive performance, and impaired mood are among the documented consequences of chronic sleep deprivation in orbit. The immune system, meanwhile, is working harder than normal and becoming, paradoxically, less effective. The combination of radiation exposure, psychological stress, disrupted sleep, altered nutrition, and other spaceflight stresses produces a complex and not fully predictable effect on immune function. Some studies have found that the immune system goes into a kind of hyperactivation state in space, with elevated levels of certain inflammatory markers. Others have found evidence of reduced immune surveillance and impaired ability to respond to certain pathogens. Latent viruses that exist in a dormant state within the body after a past infection, including several members of the herpes virus family, have been documented to reactivate in astronauts during spaceflight at higher rates than on Earth. The Epstein-Barr virus, cytomegalovirus, and varicella-zoster virus, the virus responsible for chickenpox and shingles, have all been detected at higher rates in astronaut samples during and after missions. The clinical significance of this reactivation in the controlled environment of a spacecraft with a small, isolated crew is generally low, but it speaks to the real immunological stress that the body is experiencing, and the skin itself changes. Astronaut reports and clinical observations have noted that skin becomes thinner during spaceflight, more fragile and slower to heal when injured. Without the constant mechanical stimulation of gravity on the epidermis and dermis, the skin loses some of its structural stimulus, thinning and becoming more easily damaged. Wound healing, which is already a complex multi-step process dependent on adequate blood flow, cellular migration, and tissue remodeling, becomes less efficient in the microgravity environment. Minor cuts and abrasions, the kind that would be trivial on Earth, can take longer to heal in orbit and require more attention. The cardiovascular system continues its adaptation over the first weeks and months. Beyond the initial fluid redistribution and the rapid reduction in plasma volume, the heart itself begins to change. Without the constant work of pumping blood against gravity, the cardiac muscle, like all muscles deprived of their normal load, begins to atrophy. The mass of the left ventricle, the primary pumping chamber of the heart, has been documented to decrease during long-duration spaceflight. The heart, literally, shrinks. This change, which is referred to as cardiac atrophy, has real consequences for the astronaut's ability to function when they return to a gravitational environment. Post-flight, many returning astronauts experience orthostatic intolerance, an inability to maintain adequate blood pressure when standing upright. Blood pools in the legs after landing. The heart, now smaller and less efficient, cannot pump it up to the brain quickly enough. Dizziness, lightheadedness, and in some cases fainting can result. This is why returning astronauts from long-duration missions are typically carried from their landing craft rather than walking immediately, their cardiovascular systems requiring time and rehabilitation to readapt to the demands of life with gravity. Within the first weeks of orbital life, the body is also beginning to reckon with what we might call the sensory poverty of space. Touch, smell, and taste are all affected. The nasal congestion caused by the cephalad fluid shift alters the sense of smell, and consequently the experience of taste. Food that astronauts enjoyed on Earth often tastes blander in orbit. This is why NASA and other space agencies work to include strongly flavoured, well-seasoned foods in mission menus, accommodating the documented tendency of astronauts to seek out spicy or otherwise intense flavours during their time in orbit. Touch itself changes somewhat, as the perpetual absence of contact with a surface, of the grounding sensation of the floor beneath your feet, of the pressure of a chair beneath you, removes a constant background of tactile information that the brain normally processes without awareness. The experience of orientation in three-dimensional space also transforms in ways that are difficult to describe to those who have not experienced it. On Earth, up and down are absolute and obvious. In the space station, they are arbitrary. The station itself has a defined orientation with a floor and a ceiling, but there is no physical reason why one direction should feel more natural than another. Astronauts describe gradually learning to navigate the station according to visual and contextual cues rather than any felt sense of gravity. Some adapt quickly and find the experience liberating. Others find the perpetual absence of any gravitational orientation subtly but persistently unsettling, a background discomfort that never quite disappears during their time in orbit. And then there is the psychological dimension, which is sometimes treated as secondary to the physical transformations but is in fact deeply intertwined with them. The experience of confinement, of isolation from everyone and everything familiar, of working in a high-stakes, high-pressure environment with a small group of colleagues for months without the ability to simply leave, of being separated from the Earth by hundreds of kilometers of vacuum, is genuinely extraordinary. Researchers studying the psychological effects of long-duration spaceflight have documented a range of challenges including mood disturbances, cognitive fatigue, interpersonal tensions within crews, and a phenomenon sometimes called third-quarter syndrome, a dip in morale and motivation that tends to occur roughly 3/4 of the way through a long mission, when the initial novelty has long since faded and the end is not yet close enough to provide its own psychological lift. NASA and other agencies invest significant resources in countermeasures for these psychological challenges, including regular communication with family members, psychological support from a dedicated ground-based team, carefully designed work schedules that provide adequate rest and variety, and attention to mission nutrition, environment, and social dynamics. The evidence suggests that these countermeasures help, but they cannot eliminate the fundamental psychological weight of long-duration isolation in an extreme environment. All of this is unfolding in a person who, at the moment of MECO, may have been in the best physical condition of their life. Astronaut candidates face one of the most demanding selection processes in the world, competing against thousands of applicants for a handful of positions. Those who are selected spend years in training, are assessed continuously for physical and psychological fitness, and arrive at the launch pad as among the most carefully screened and thoroughly prepared human beings in existence. And yet within hours of entering orbit, their body's already reshaping itself, abandoning adaptations that took billions of years to develop, reconfiguring itself for an environment that human biology was never designed to inhabit. The question that has driven space medicine research since the earliest days of human spaceflight, and that drives it still, is this: how far can the body be pushed, and how do we keep it healthy enough to go further? Because going further is the entire point. The International Space Station is a proving ground, a platform for understanding what spaceflight does to the human organism, so that we can develop the countermeasures and the knowledge needed for the journeys that come next. The Moon, which takes approximately 3 days to reach from Earth's surface, puts astronauts beyond the full protection of Earth's magnetosphere, but still within a distance from which emergency return is theoretically possible within days. Mars, which at its closest approach is still roughly 55 million kilometers away, is a different proposition entirely. A one-way transit to Mars would take 6 to 9 months depending on trajectory and propulsion technology. The crew would be entirely beyond any possibility of emergency rescue. They would be soaking in galactic cosmic radiation every day of that transit. They would be losing bone and muscle. Their eyes might be changing. Their immune systems would be working differently. Their sleep would be disrupted. Their hearts would be shrinking. And yet, remarkably, people have done it. People are doing it right now, aboard the International Space Station, conducting the research that will make those future journeys possible. The story of how we have learned what we know, and how much we still do not know, is itself a testament to the extraordinary ambition of human curiosity and the remarkable resilience of the human organism. Let us go deeper into the biology, because there are layers to what space does to the body that we have not yet explored, and some of them are among the strangest things that happen to a person in the history of their biological existence. Consider what happens to the distribution of mass in the body over the first weeks of orbital life. We have discussed how fluid moves from the lower extremities toward the head and chest, but there is a related phenomenon happening to fat tissue, to circulating proteins, and to the cellular communication networks that regulate metabolism. The body's metabolic state changes in space in ways that are not simply explained by reduced activity or altered caloric intake. Inflammatory markers in the blood, proteins called cytokines that regulate the immune response and tissue repair, shift in their concentrations and their activity patterns. Some studies of ISS crew members have documented elevated levels of certain pro-inflammatory cytokines, suggesting a systemic state of low-grade inflammation that persists throughout long-duration missions. This kind of chronic low-grade inflammation is associated on Earth with a range of health problems, including cardiovascular disease and metabolic disorders, and its presence in orbiting astronauts is a finding that researchers are tracking carefully. The mitochondria, the organelles within cells that generate the energy currency that powers cellular processes, also appear to be significantly affected by the spaceflight environment. Research published in peer-reviewed journals, based on detailed proteomic analysis of muscle tissue from ISS astronauts, has documented dramatic downregulation of mitochondrial proteins during spaceflight, particularly components of the inner mitochondrial membrane where the energy-generating chemical reactions take place. The researchers describe this mitochondrial disruption as one of the primary cellular-level consequences of extended spaceflight, and hypothesized that it may be driven not simply by the mechanical unloading of weightlessness, but by the reactive oxygen species, the chemically reactive molecules containing oxygen, that are generated in elevated quantities in cells exposed to radiation and other spaceflight stressors. In other words, the cellular energy factories in the muscles may be damaged by the radiation environment of space in ways that compound the mechanical damage done by the absence of gravitational load. This matters enormously because mitochondrial function is central to virtually every aspect of cellular health. When mitochondria are impaired, the cells they power are impaired. Muscles with damaged mitochondria become weaker, not just because of atrophy, but because their remaining fibers cannot generate energy efficiently. The implications ripple outward: reduced physical performance, impaired immune cell function, altered metabolism, and a general decrease in the biological resilience that the body needs to cope with everything else the spaceflight environment is throwing at it simultaneously. There is also the matter of the cardiovascular architecture itself, changing at a structural level beyond the simple atrophy of the cardiac muscle. Research from the NASA twin study and other sources has documented thickening of the carotid artery walls in astronauts after long-duration missions. The carotid arteries carry blood from the heart to the brain, and changes in the structure of arterial walls are closely associated on Earth with cardiovascular disease risk. The precise mechanism by which spaceflight alters carotid artery structure is not fully established, though researchers point to radiation-induced endothelial damage, inflammatory changes, and the altered hemodynamics of the cephalad fluid shift as likely contributing factors. What is established is that these changes are real and measurable, and that their long-term implications for astronaut cardiovascular health require continued study. The retinal thickness changes documented in astronauts are another window into this vascular physiology. The retina is among the most metabolically demanding tissues in the body, and it is richly supplied with blood vessels. Changes in retinal thickness detected by optical coherence, tomography in ISS crew members suggest alterations in the choroidal blood supply, the vascular layer beneath the retina, consistent with the elevated pressure and altered flow dynamics produced by the cephalad fluid shift. When you think about the eye changes in space, the thickening of the retina and the flattening of the globe and the swelling of the optic disc, you're looking at the visible manifestation of a broader systemic vascular disruption that is affecting blood flow and pressure throughout the upper body. Now, the body is an extraordinary problem-solving machine, and it does not simply suffer these changes passively. It adapts. Heat shock proteins, molecular chaperones that help cells cope with stress by preventing the misfolding of damaged proteins and assisting in cellular repair, are upregulated in the spaceflight environment. Research into microgravity and heat shock proteins has shown that these protective molecules are more active in cells exposed to conditions simulating weightlessness, suggesting that the body is mounting a genuine cellular defense against the stresses it is experiencing. Some researchers believe that understanding how to enhance this heat shock protein response pharmacologically could provide a way to improve astronaut resilience during long-duration missions. The bone marrow, where red blood cells are produced, is affected by spaceflight in a way that contributes to a condition researchers have called space anemia. Studies have documented a reduction in the production of red blood cells early in a mission, possibly because the cardiovascular system's initial interpretation of the cephalad fluid shift as a fluid overload signal leads to a suppression of the hormones that stimulate red blood cell production. When the total volume of plasma in the bloodstream decreases, the relative concentration of red blood cells might be maintained or even increased, but the absolute number of circulating red blood cells decreases. This reduction in red cell mass can contribute to fatigue and reduced aerobic capacity, adding to the constellation of challenges the astronaut's body is managing. There is also, quietly and consistently throughout a mission, the matter of how the absence of gravity changes the flow of air within the respiratory system. On Earth, the weight of the lung tissue itself and the weight of the abdominal organs pressing up against the diaphragm creates a gradient in how air is distributed through the lung's different regions. The lower portions of the lungs tend to be better perfused with blood than the upper portions under normal gravitational conditions. In weightlessness, this gradient disappears, and the distribution of both air and blood through the lung tissue changes. For most astronauts in normal health, this does not produce clinical respiratory problems, but it is a physiological change with potential implications for how medications delivered by inhalation are absorbed, for how the lungs respond to dust or particulate matter in the cabin environment, and for the respiratory dynamics of any astronaut with underlying conditions. The cabin environment itself deserves a brief discussion, because it is a factor that interacts with all the physiological changes we've been describing. The air inside the International Space Station is maintained at roughly sea level pressure, approximately 1 atmosphere, and at a comfortable temperature. The gas mixture is carefully regulated to maintain the appropriate concentrations of oxygen, nitrogen, and carbon dioxide. But maintaining ideal air quality in a closed system where multiple people are breathing, exercising, cooking, and working requires constant management, and the carbon dioxide levels inside the station can drift upward to concentrations that, while not immediately dangerous, are higher than those experienced on Earth and have been associated in some studies with headache, mild cognitive effects, and reduced sleep quality in astronauts. This represents another layer of biological challenge layered on top of everything else. The air itself is subtly different from what the body evolved to breathe. The question of nutrition in space deserves attention as well, because the relationship between diet and physiology in the microgravity environment is complex and important. Astronauts can lose body mass during long-duration missions, sometimes significantly. Reduced appetite, the altered sense of taste and smell produced by nasal congestion, the disruption of normal meal rhythms, and the physical changes in gastrointestinal motility caused by weightlessness all contribute to this. Without gravity to help propel food through the digestive system, peristalsis, the wave-like muscular contractions that move food through the intestines, works against a different mechanical background. Gas management becomes more challenging, which is why increased flatulence is documented as a common early symptom. The absorption of certain nutrients may be affected. The elevated calcium excretion linked to bone loss needs to be carefully managed in the diet to prevent its contribution to kidney stone formation. NASA food scientists work to develop menus that are palatable, nutritionally complete, shelf-stable, and practical to eat in a weightless environment, where small particles that float free can be inhaled or can damage sensitive equipment. Tortillas have long been favoured over bread for this reason. Meals are carefully formulated with attention to macronutrient balance, micronutrient content, and caloric density. And yet even with these careful preparations, astronauts commonly lose weight during missions, particularly during the early adaptation phase, and maintaining adequate nutritional status across a long mission remains an active research and operational challenge. As we continue to understand the full scope of what space does to the human body, it is worth pausing to appreciate how much of what we know comes from the courage and the generosity of the men and women who have volunteered as research subjects. Every mission to the International Space Station is also, in a very real sense, a medical study. The astronauts who fly today submit to blood draws before and after missions, allow researchers to analyse their urine and saliva and exhaled breath, consent to ultrasound imaging of their spines and eyes and hearts, undergo cognitive testing, and contribute samples to studies that they know may take years to fully analyse. The data they generate is the foundation of everything we're discussing today, and of everything that future space travellers will benefit from. This is also a good moment to note that much of the research in this field is genuinely recent. The detailed molecular level understanding of what radiation does to individual cells, the discovery of the SAMS syndrome and its ocular consequences, the comprehensive genomic picture provided by the twin study, the detailed mapping of mitochondrial changes in space. These are findings that have emerged in the last 2 decades, and in some cases the last few years. Our understanding is accelerating. New technologies for in-flight health monitoring, new imaging modalities, new genomic and proteomic tools are giving researchers capabilities that simply did not exist in earlier decades of spaceflight. The picture we have today of what space does to the human body is vastly more detailed and nuanced than what was available even 20 years ago, and it will be vastly more detailed again in 20 years' time. As always on this channel, we encourage you to stay curious, to follow the primary research, and to treat our current understanding as the best available map of the territory, not the final word on it. We should also speak honestly about the fact that most of the long-duration spaceflight data we have comes from a relatively small number of individuals, all of whom were selected for exceptional fitness and health, and all of whom spent their time in the relatively sheltered environment of low Earth orbit, still partially protected by Earth's magnetic field. The physiological responses to a multi-year deep space mission, conducted entirely beyond Earth's magnetosphere, in the full intensity of the interplanetary radiation environment, are not something we have yet directly measured in human beings. The animal studies, the ground-based simulations, the models built from ISS data, all contribute to our projections, but they are projections, and the actual human experience of a long-duration deep space voyage will contain surprises. Some of those surprises may be better than we expect. Some may be worse. The honest scientific position is that we do not yet fully know. What we do know is that the body that leaves Earth on a voyage to Mars will not be the same body that arrives there. It will have been reshaped at every scale from the molecular to the anatomical, by months of weightlessness and radiation, and disrupted sleep and fluid redistribution and immunological stress. The people who make that journey will do so carrying the full weight of what 6 decades of space medicine research have taught us about human physiology, armed with the best countermeasures science can currently devise, monitored with the most sophisticated health tracking technology available, and they will still be entering the unknown. That is, in a way, exactly what exploration is. The human body has surprised us before. In the early days of the space age, there were serious scientific concerns about whether human beings could function at all in weightlessness. Some researchers worried that the absence of gravity would prevent swallowing, that food and fluids would not pass from the mouth to the stomach without gravity's assistance. Others worried about whether the cardiovascular system could maintain blood flow to the brain in the absence of gravitational gradients. These fears proved unfounded. The body adapted, found new mechanisms, constructed new equilibria. It did so imperfectly, and at real biological cost, but it did so. That capacity for adaptation, rooted in the same evolutionary plasticity that allowed our distant ancestors to colonize every continent on Earth and survive in conditions ranging from polar ice to equatorial desert, is our most important tool for space exploration. The human body was not built for space. That is simply, unambiguously true. But it is also capable of going there, of surviving there, of working there, and of returning. And with each mission we learn a little more about how to do it better, how to protect the bones and preserve the muscles and shield the eyes, and support the immune system, and manage the radiation exposure and maintain the psychological health of the people we're asking to leave their planet behind. The story of what happens to the body in space is, at its core, a story about the extraordinary gap between where evolution brought us and where our curiosity is trying to take us. It is a story about the lengths to which the human organism will go to maintain itself in an environment it was never designed for, and it is a story that is still being written, in orbit right now, by the people floating above us who are simultaneously doing the most demanding jobs in the world and serving as living research subjects in the most ambitious scientific enterprise our species has ever undertaken. There is still a great deal more to understand about this story. The changes we have covered today represent the opening chapters of a physiological saga that plays out differently in different individuals, that deepens and compounds over months, that reverses itself partially and imperfectly after landing, and that leaves traces in the biology of returning astronauts that researchers are still working to characterize and understand. The brain changes, the gut changes, the eye continues its slow reshaping, the immune system navigates its complex recalibration. And out in deep space, in the territory beyond the magnetosphere's protection, entirely new chapters begin to unfold. The brain changes. Of all the transformations that space imposes on the human body, the ones occurring inside the skull are perhaps the most unexpected, the most profound, and in some ways the most difficult for people to fully appreciate when they first encounter the research. We talk about bones and muscles and fluids and radiation, as if the brain stands apart from all of that, as if the 3-pound organ responsible for every thought and memory and perception remains a stable observer of everything happening around it. But the brain does not stand apart. It is tissue, suspended in fluid, connected by blood vessels, dependent on pressure gradients, sensitive to everything the body experiences, and in the microgravity environment of space, the brain changes in ways that neuroimaging has only recently made visible. Let us begin with something that sounds almost impossible the first time you hear it. When a person spends months in space, their brain physically moves inside their skull. On Earth, the brain sits within the cranial cavity and is surrounded by cerebrospinal fluid, a clear, colourless liquid that cushions it, carries away metabolic waste, and provides a mechanical buffer against impact. Gravity keeps the brain gently settled toward the bottom of this cavity. In weightlessness, the same cephalad fluid shift that pushes blood and lymphatic fluid toward the head also redistributes the cerebrospinal fluid. Studies using magnetic resonance imaging have documented that astronauts returning from long-duration missions show evidence of an upward and backward displacement of the brain within the skull. The brain, freed from gravity's downward anchor, rides the rising tide of fluid and shifts position. Research published by multiple teams over the past decade, drawing on MRI data from NASA, ESA, and Roscosmos astronauts, has consistently found this upward brain displacement as a characteristic feature of long-duration spaceflight. This shift is not a massive or dramatic movement. We're talking about structural changes that only become apparent through careful before and after imaging, but its consequences may be significant. The superior sagittal sinus, a large venous channel that runs along the top of the brain and is one of the primary drainage routes for cerebrospinal fluid, can be compressed by the brain moving toward it. The arachnoid granulations, tiny structures along this sinus that absorb cerebrospinal fluid back into the venous circulation, may have their function impaired when they are compressed. If cerebrospinal fluid resorption slows, pressure within the cranial cavity builds. This is the proposed link between the upward brain shift and the elevated intracranial pressure that researchers believe contributes to SANS, the vision syndrome we discussed earlier. Alongside this physical repositioning, the ventricles of the brain, the fluid-filled cavities at its interior, expand substantially. Measurements from ISS missions have found average ventricular volume increases of approximately 17 to 24% on the left and right sides after 6-month missions, and even larger increases after 12-month missions. One astronaut who completed a 12-month mission showed left ventricular expansion of 25% and right of 23%. These are not small numbers. On Earth, progressive ventricular enlargement is associated with neurodegeneration and is a feature of conditions like normal pressure hydrocephalus. In space, It appears to reflect a compensation for the altered cerebrospinal fluid dynamics produced by the fluid shift, a structural adaptation as the brain's fluid system tries to accommodate its new environment. The troubling finding is that these ventricular changes do not fully resolve after landing. Studies that followed astronauts for 6 months after returning to Earth found that while many brain structure changes returned to baseline, the ventricular expansion showed little recovery. Researchers noted that astronauts with less time between subsequent missions showed larger pre-flight ventricular volumes than those with longer gaps, suggesting that the effects of one mission may not have fully resolved before the next mission begins. The long-term significance of persistent ventricular enlargement in the brains of astronauts is an open and important question. On Earth, the analog condition most studied in relation to spaceflight-associated neuroocular changes is idiopathic intracranial hypertension, and researchers continue to investigate whether the ventricular changes seen in astronauts carry any of the same clinical risks. Beyond the fluid dynamics, the white matter of the brain itself shows measurable changes after spaceflight. White matter is the connective tissue of the brain, bundles of myelinated nerve fibers that transmit signals between different brain regions and between the brain and the rest of the nervous system. It is the wiring that makes coordination, balance, sensory integration, and cognitive function possible. Diffusion magnetic resonance imaging, a specialized technique that maps the movement of water molecules within brain tissue, allows researchers to assess the microstructural integrity of white matter without opening the skull. Studies using this technique on astronauts before and after missions have found changes in white matter microstructure, particularly in tracts associated with vestibular function, visual processing, visuospatial awareness, and sensoromotor control. These are precisely the neural pathways most challenged by the experience of weightlessness and by the sensory conflicts that space generates. A 2019 study published in the journal JAMA Neurology found that white matter microstructural changes in astronauts after long-duration spaceflight were of a greater magnitude than those typically seen in healthy people over the same time period through normal aging. This comparison is sobering. Aging produces gradual, well-characterized changes in brain white matter. Space appears to produce similar but accelerated changes, compressed into a mission duration far shorter than the years over which age-related changes typically accumulate. And there is the matter of the perivascular spaces, tiny fluid-filled channels that surround blood vessels as they pass through brain tissue. These spaces are part of the brain's waste clearance system, helping to remove metabolic byproducts that accumulate during neurological activity. Research published in 2022 found that astronauts who had no prior spaceflight experience showed an increase in perivascular space dimensions after their first mission, while experienced astronauts with prior flight time did not show the same change. This finding is intriguing in several directions at once. It might reflect a compensatory adaptation in the waste clearance system, responding to altered cerebrospinal fluid dynamics. It might reflect a prior structural change from earlier missions that persisted and altered the baseline. The researchers were careful to note that it is unclear whether these changes in perivascular space represent a compensatory mechanism or could eventually lead to pathological changes with cumulative exposure. What it suggests, very clearly, is that the brain's fluid management system is being reorganized by spaceflight in ways that depend on an individual's specific history of exposure. The question that naturally arises from all of this neuroimaging data is the one that matters most to the people who actually go to space. Does any of it affect how the brain functions? Do these structural changes impair thinking, memory, and perception? The honest answer is that the research on cognitive performance during and after spaceflight is, as one major review paper put it, largely inconclusive. The practical challenge is significant. Measuring cognitive function requires reliable, sensitive tests administered under standardized conditions. Doing that in orbit, with crew members under operational pressure, in an environment full of confounding stresses, including sleep deprivation and workload and confinement, is technically difficult. The available evidence includes some findings of modest cognitive decrements. The NASA twin study documented that Scott Kelly showed significant decrements in performance on neurocognitive assessments after his 340-day mission, compared with both his own pre-flight baseline and his twin brother's performance on Earth. Some astronauts and researchers have described a phenomenon informally called space fog, a subjective sense of slightly blunted cognitive sharpness during long missions. But overall, The formal evidence for major cognitive impairment in current long-duration astronauts is not robust, and most brain function changes appear to resolve within 1 to 6 months of returning to Earth. That last point about recovery is important and is itself among the most carefully studied questions in spaceflight neuroscience. Research by Rachel Seidler and colleagues at the University of Florida, who have studied spaceflight's effects on the brain across multiple astronaut cohorts, has found that the brain demonstrates remarkable compensatory plasticity after spaceflight. When astronauts return to Earth and undergo functional neuroimaging while performing tasks that require coordination or cognitive processing, their brains show patterns of neural recruitment that were not present before the mission, engaging additional pathways to achieve task performance. This additional neural recruitment is the brain's adaptation strategy, consciously or unconsciously drafting reserve circuitry into service to compensate for whatever changes spaceflight has produced in the primary pathways. Over the weeks and months of post-flight recovery, as the body readapts to gravity and the structural changes begin to resolve, this compensatory pattern gradually fades and the brain returns to its pre-flight functional organization. This finding carries an important implication for future missions. The brain can compensate. But compensation is not the same as baseline function. A brain that is recruiting additional pathways to maintain performance is a brain working harder than it would be otherwise, drawing on reserves that might be needed for other demands. For a crew member on a long transit to Mars, operating complex systems, making critical decisions, managing emergencies, and maintaining the precise performance standards that spaceflight requires, any reduction in cognitive reserve, even one that has not yet crossed a clinical threshold, is a consideration that mission planners take seriously. Now let us look at what happens to the body as it prepares to return to Earth, because the second transition, from weightlessness back to gravity, is in some ways as demanding as the first. After months of weightlessness, the body has reached a new equilibrium. It has redistributed its fluids, it has reduced its blood volume, its cardiovascular system has remodeled, its muscles have shrunk and its bones have thinned, its brain has moved upward and its ventricles have expanded, its spine has elongated, its immune system is running on a different profile, its gene expression patterns have shifted. In physiological terms, it has become an efficient machine for living in weightlessness, at the cost of becoming less well suited for living on a planet with gravity. And then, in the final hours of the mission, it must prepare to reverse almost everything it has done. The re-entry sequence itself is physically brutal. As the spacecraft hits the upper atmosphere and begins to decelerate, the crew once again experiences increasing g-forces. For a Soyuz return, which is the vehicle that brings most long-duration ISS crew members home, the deceleration can produce forces of 3 to 4 Gs during the most intense phase of atmospheric braking, sustained for several minutes. For a body that has not felt any gravitational load for 6 months, 3 to 4 Gs is not merely uncomfortable, it is genuinely shocking. The cardiovascular system, which has spent months reducing its capacity to pump blood against gravity, is now being asked to pump against gravity that is several times stronger than the one it adapted away from. Blood rushes to the lower extremities. The heart, smaller and weaker than before launch, struggles to maintain adequate blood pressure to the brain. Many returning astronauts experience a profound lightheadedness during and immediately after landing, some approaching or reaching orthostatic syncope, a near faint caused by insufficient blood flow to the brain. The moment of touchdown brings another sudden shift. Gravity, absent for so long, arrives all at once and in full force. Limbs that have been weightless feel impossibly heavy. Astronauts who have spent 6 months in space describe the experience of feeling their own head as a weighty object their neck must support, an effort that their weakened neck muscles have largely forgotten how to make. Frank Rubio, who set the American record for a single spaceflight at 371 days when his originally planned 6-month mission was involuntarily extended after a micrometeoroid struck and disabled his return vehicle, was lifted from his capsule by recovery personnel upon landing in Kazakhstan in September 2023. He and his crewmates could not walk unassisted. After nearly a year in orbit, the very act of standing upright under Earth's gravity was beyond their immediate capacity. Rubio described his experience in an interview, explaining that his body adjusted to gravity's return more quickly than he expected, thanks to the intensive exercise regimen he had maintained throughout his extended mission. He said he felt mostly recovered within a couple of weeks. But he also acknowledged that the psychological dimension of spending nearly a year in space was tougher than he had anticipated, that missing the milestones of his children's lives, the graduations and the beginnings of college, had been genuinely hard. His honest reflection on this is a reminder that the costs of long-duration spaceflight are not only physiological. The post-landing rehabilitation program at NASA is structured, intensive, and begins immediately. The astronaut strength, conditioning, and rehabilitation specialists implement a reconditioning protocol that runs 2 hours per day, 7 days a week, for 45 days after landing. The program is individualized, calibrated to each astronaut's specific test results, medical status, and mission role. Early sessions focus on the fundamentals, learning to walk without falling, re-establishing the proprioceptive signals that tell the brain where the body's limbs are in space, rebuilding cardiovascular endurance, and restoring the core stability that months of reduced loading have eroded. As weeks pass, the sessions advance to strength training, balance challenges, and more complex movements. The goal is to return each astronaut to their pre-flight physical condition, which for some systems is achieved relatively quickly, and for others takes considerably longer. Muscles recover fastest, typically within 1 to 2 months of intensive post-flight training. The neuromuscular system, which coordinates muscle activation, responds quickly to training stimuli, and the muscular atrophy of even a 6-month mission can be substantially reversed with several weeks of consistent loading. Cardiovascular fitness follows a similar trajectory. The heart remodels back toward its pre-flight size as it re-encounters the daily demands of supporting a body standing and moving in gravity. Blood volume, which had been reduced in orbit, increases again as the kidneys respond to the new hydrostatic signals and retain more fluid. Balance and coordination take longer, typically several weeks of persistent rehabilitation, before the vestibular system and the brain sensoromotor processing can be trusted to navigate complex environments reliably. The brain, which adapted so thoroughly to weightlessness that it began to suppress the vestibular input it could no longer use, now has to relearn how to integrate inner ear signals with visual and proprioceptive information to maintain stable, upright posture. Some returning astronauts describe the sensation of Earth as almost overwhelmingly heavy and loud and still after the perpetual floating and the constant hum of the space station, the silence of an empty room, the strange heaviness of a glass of water, the disconcerting sensation of the ground pushing up against the soles of their feet. Bone recovery is the longest and most uncertain. After a 3 to 4 month mission, research suggests it takes approximately 2 to 3 years to fully recover lost bone density. After a year or more in space, the timelines extend further, and the recovery may not be complete. The weight-bearing bones of the lower skeleton, those that received the strongest stimulus from daily gravitational loading on Earth, lost the most during the mission and require the most sustained rehabilitation to rebuild. Weight-bearing exercise is the primary driver of bone recovery on Earth, so the reconditioning program focuses heavily on progressive loading activities that stimulate the osteoblasts to rebuild what the osteoclasts have dissolved. Meanwhile, the eyes require careful monitoring for months after return. As the body re-establishes normal fluid dynamics in a gravitational environment, the intracranial pressure that had been elevated during the mission begins to normalize. The ventricular expansion that persisted after landing slowly resolves for some astronauts, though as we discussed, it does not always return fully to pre-flight levels. Visual acuity, which may have been blurred or shifted toward farsightedness during the mission, due to the globe flattening and optic disc changes of SAS, typically improves after landing, but may not return entirely to the pre-flight baseline in astronauts who experience the most significant changes. Some have required updated prescriptions for glasses years after landing, the lasting legacy of the fluid physics of orbit written into the structure of their eyes. The immune system gradually recalibrates after return to Earth. The latent viruses that reactivated in orbit return to dormancy. The inflammatory markers that were elevated during the mission trend back toward normal ranges. The gene expression changes documented in the twin study mostly resolved within hours to days of landing, though the approximately 7% that remained altered at 6 months post-flight suggests that some biological changes persist in ways that current understanding cannot yet fully characterize. This brings us to a central question for the future of human spaceflight, and it is one that space medicine specialists, mission planners at NASA and ESA, and the broader scientific community are grappling with increasing urgency. The International Space Station was never meant to be a permanent solution. It is scheduled for decommissioning sometime in the late 2020s or early 2030s. The Artemis program is actively working toward returning astronauts to the surface of the Moon, where they would experience approximately 1/6 of Earth's gravity, a partial gravity environment that presents its own set of physiological questions that current long-duration studies cannot fully answer. And beyond the Moon, Mars waits, with its surface gravity of roughly 38% of Earth's, its crushing radiation environment, its chemical dust, and its extraordinary distance from any possible rescue or resupply. A crewed Mars mission under current propulsion technology would expose astronauts to a radiation dose during transit that alone might approach or exceed the career exposure limits set for ISS astronauts. Research from the Curiosity rover's radiation assessment detector, which measured the radiation environment during its transit to Mars and on the Martian surface, provided the first direct measurements of the radiation dose a human crew would experience on a Mars mission. The data suggested that a round-trip mission would expose the crew to a cumulative dose of approximately 1 sievert of radiation, well above the levels considered acceptable for prolonged occupational exposure on Earth and sufficient to meaningfully increase lifetime cancer risk. Researchers studying the highest priority health risks for a Mars mission have categorized radiation as a red risk, the most serious category, alongside behavioral health issues associated with the isolation and confinement of deep space transit. The engineering response to these risks is evolving. Pharmaceutical approaches to protecting bone density during spaceflight have made progress. Bisphosphonate medications, the same class of drugs used to treat osteoporosis on Earth, have been shown in NASA studies to be effective in slowing bone loss during spaceflight when combined with the exercise regimen. Researchers are investigating additional pharmaceutical countermeasures for muscle atrophy, immune dysregulation, and radiation protection, including drugs that might enhance the DNA repair machinery of cells or reduce the inflammatory damage caused by radiation exposure. Artificial gravity, long a staple of science fiction spacecraft, is under serious scientific consideration as a potential countermeasure for the full spectrum of physiological challenges associated with long-duration weightlessness. The concept is straightforward in principle. A spacecraft that rotates produces a centrifugal force that simulates gravity for the crew inside it. The challenges are substantial in practice. The rate of rotation required to produce a meaningful gravitational substitute creates its own vestibular complications, as any movement of the head in a rotating environment generates Coriolis forces that can cause disorientation and nausea. The engineering mass and volume required for a rotating habitat section adds significantly to mission cost and complexity. And the optimal parameters, the ideal rotation rate, radius, and duty cycle that would provide sufficient gravitational stimulus without causing intolerable vestibular side effects, are still being worked out in ground-based centrifuge studies. Research into short-radius centrifugation, where a crew member lies on a small rotating platform for intermittent periods rather than living in a continuously rotating habitat, has produced promising early results. Studies suggest that relatively brief daily periods of centrifugation might provide enough gravitational loading to significantly reduce bone and muscle loss without requiring a full-scale rotating spacecraft. Several research groups are actively pursuing the optimal protocols for this kind of intermittent artificial gravity as a practical near-term countermeasure for future deep space missions. On the radiation side, the engineering challenges are even more formidable. As we discussed, conventional aluminum shielding is largely ineffective against high-energy galactic cosmic rays, and in some configurations can make the problem worse by producing secondary radiation cascades. More promising approaches include hydrogen-rich shielding materials such as polyethylene, water walls incorporated into habitat structures, and active electromagnetic shielding concepts that would create a miniature magnetosphere around the spacecraft. All of these approaches are at various stages of development and testing, and none yet represents a complete solution to the galactic cosmic ray problem for a multi-year deep space voyage. There is also growing interest in personalized medicine approaches to spaceflight health. The twin study and subsequent research have made it increasingly clear that individual variation in response to spaceflight is substantial. Some astronauts develop significant SAS symptoms while others on equivalent missions do not. Some develop more pronounced cognitive changes while others show little measurable effect. Some lose bone and muscle at higher rates than others, despite equivalent exercise protocols. Understanding the genetic, physiological, and lifestyle factors that underlie this individual variation could allow mission planners to screen candidates for particular vulnerabilities, to tailor countermeasure protocols to individual risk profiles, and perhaps eventually to identify pharmacological or other interventions that could reduce specific risks in individuals who are predisposed to them. This kind of personalized, precision medicine approach to spaceflight health is already emerging as a research priority. The same genomic and proteomic tools that made the twin study possible are being applied to larger astronaut cohorts, looking for biomarkers that predict particular health outcomes. Genetic variants associated with bone density, immune function, DNA repair capacity, and vascular health are being correlated with actual physiological changes documented during and after missions. The goal is to build predictive models that allow researchers and flight surgeons to anticipate and manage individual risks, rather than waiting for them to manifest. This science does not only matter for astronauts. Some of the most important practical applications of spaceflight health research are emerging here on Earth, in conditions that have nothing to do with rockets or orbital mechanics. The physiological changes of long-duration spaceflight turn out to be a remarkably pure experimental model for certain terrestrial medical problems. The muscle atrophy and bone loss of microgravity closely resemble the changes seen in long-term bed rest, in spinal cord injury, and in the frailty of advanced aging. Research into countermeasures for spaceflight-induced muscle loss has contributed directly to exercise protocols used in rehabilitation medicine. The study of vestibular recalibration after spaceflight has informed the understanding and treatment of balance disorders on Earth. The research into SANS and intracranial pressure has generated new insights into conditions like idiopathic intracranial hypertension, where elevated pressure in the cerebrospinal fluid system causes vision problems and headaches in people on Earth who have never been near a rocket. The gut microbiome research generated by long-duration spaceflight studies has contributed to the broader understanding of how the microbial communities in the intestine respond to extreme stress and environmental disruption. The telomere findings from the twin study have energized research into how cellular aging is affected by extreme environments and how the relationship between stress, inflammation, and telomere dynamics might be manipulated to benefit human health. Space medicine is increasingly not a specialty operating in isolation from the broader biomedical enterprise, but a source of uniquely powerful data about what happens when the human body is taken to its physiological limits. As we look toward a future that seems increasingly likely to include not just occasional government astronauts visiting low Earth orbit, but commercial passengers on brief suborbital hops, private crews venturing to the Moon, and eventually settlers attempting to establish a permanent human presence on Mars, the questions raised by decades of spaceflight health research become urgently relevant to a far broader population. The physiological challenges we have been discussing are not unique to the professional astronaut class. They are the challenges that will face any human being who leaves this planet for any meaningful period of time. The biology does not care about your ticket price or your employer. The cephalad fluid shift begins the moment weightlessness does, whether you are a career astronaut with years of training or a private citizen on your first and only voyage beyond the atmosphere. This is part of why the research being done right now on the International Space Station, in ground-based bed rest studies, in centrifuge labs and radiation biology facilities around the world, matters so much. The science being conducted by the men and women floating 400 kilometers above us is not simply satisfying academic curiosity about what space does to the body. It is building the knowledge base that will determine whether human beings can safely explore and eventually inhabit other worlds. Every measurement, every scan, every blood draw and urine sample and bone density assessment contributes to a growing body of evidence that will guide the medical protocols, the spacecraft designs, the habitat architectures, and the mission structures of future deep space exploration. The stakes could not be higher. And there is something else worth pausing to consider, something that tends to get lost in the clinical language of physiological measurements and countermeasure protocols and risk assessments. The human beings who have experienced all of this, who have lived through the fluid shifts and the vestibular rebellion, and the bone loss and the radiation and the cognitive fog and the strange floating dreams and the puffy face in the mirror and the slowly changing eyes, have also experienced something that no amount of research data can fully capture. They have seen the Earth from orbit. They have watched it rotate beneath them, blue and white and impossibly beautiful, 16 times in every 24 hours, a planet that looks like a thing worth protecting, worth cherishing, worth the extraordinary effort of learning how to leave it and return. Astronaut after astronaut across 6 decades of human spaceflight has described this experience in terms that hover between the scientific and the philosophical, between the embodied and the transcendent. The overview effect, as it has come to be called, is the shift in perspective that seems to come over many astronauts when they first look back at the Earth from space. The arbitrary lines between nations, invisible from orbit. The thin blue line of the atmosphere, impossibly fragile against the blackness beyond. The silence of a universe that does not, from this distance, appear to be concerned with human affairs. This experience is real. It is documented. It changes people. And it is happening at the same time as all the biology we have been discussing, in the same body, to the same person. The human being floating in the space station, whose bones are quietly thinning, and whose vestibular system is learning a new set of rules, and whose DNA is registering the passage of cosmic rays, is also looking out the cupola window at the Terminator line sweeping across the Pacific and feeling something that there are not quite adequate words for. Science and wonder, it turns out, are not alternatives. They are companions. Everything we know about what space does to the body, all the data, all the measurements, all the carefully documented changes and countermeasures and recovery timelines exist because people agreed to go. They agreed to strap themselves to a column of controlled explosions and ride it above the atmosphere and float for months in a machine the size of a house, while their bones dissolved and their faces swelled and their brains moved inside their skulls. They did this knowing the risks, having studied them more carefully than anyone, and most of them, when asked, say they would do it again. There is a word for that willingness, that combination of rational risk assessment and irrational commitment to the larger goal. We might call it courage. We might call it scientific dedication. We might call it the same impulse that drove every explorer in history who has ever stood at the edge of the known and decided to walk forward anyway. Whatever we call it, it is what made the science possible. And the science, in turn, is what will make the next journey possible, and the one after that. The frontier is not closed. It has simply moved upward. That is the extraordinary truth that emerges from 6 decades of sending human beings into space and watching, with every scientific tool available, what happens to them when they get there. The body changes, sometimes dramatically, sometimes in ways that are uncomfortable, even alarming, even potentially irreversible in their long-term effects. The spine lengthens and the bones thin, and the muscles shrink and the eyes reshape and the brain moves and the genome reacts and the immune system reorganizes and the telomeres do something nobody expected. All of this is real, documented, measured, and yet people go. And they come back, and most of them come back in good enough condition to live healthy lives, to pursue active careers, to report that the experience was worth every biological cost. Scott Kelly, after 340 days in orbit, returned to Earth and eventually ran a marathon. Frank Rubio, after 371 days, felt mostly recovered within weeks. The Russian cosmonaut Oleg Kononenko has spent more time in space than any human being in history, across 5 missions totaling more than 1,000 days, and continues to fly. Valery Polyakov spent 437 consecutive days aboard the Mir space station in 1994 and 1995, a record for continuous single-mission spaceflight that still stands more than 3 decades later, and he walked off the landing site unassisted. The human body is more resilient than the stresses placed upon it by current spaceflight. That is the bottom line, backed by data. But it is a conditional resilience, one that depends on careful preparation, rigorous countermeasures, constant monitoring, and the accumulated wisdom of decades of space medicine research. Remove any of those supports and the margin narrows rapidly. For the Moon, with its partial gravity, its surface radiation environment, that is significantly more intense than the ISS due to the absence of Earth's magnetic protection, and its potential for habitat dust contamination from the abrasive regolith, new physiological challenges await that ISS research only partially prepares us for. For Mars, with its much longer exposure times, its even greater distance from medical rescue, and its full suite of physiological hazards including everything we have discussed plus the unknown biological effects of spending extended time in a partial gravity environment that is neither weightlessness nor Earth normal, the medical challenges are in a different category entirely. These are not reasons not to go. They are reasons to prepare, to research, to develop the countermeasures and the habitats, and the medical protocols and the pharmaceutical interventions that will give the people who go the best possible chance of returning healthy. Space medicine is not a discipline that exists to identify reasons to stay home. It is a discipline that exists to ensure that when we go, we know what we are walking into, and we have done everything science can do to protect the people brave enough to walk. The story of what space does to the human body is ultimately a story about limits. Not limits in the sense of barriers that say you may not pass, but limits in the sense of the edges of what we currently understand and what we currently know how to manage. The history of medicine is a history of pushing those limits back, one study, one clinical trial, one broken assumption at a time. And the history of space exploration is, among other things, a history of the human species learning what it means to take a body that evolved for one planet and ask it to survive somewhere else. That project is underway. It has been underway for 6 decades. And it is only just beginning to reveal the full scope of what it requires and what it makes possible. We hope today's deep dive into the physiology of spaceflight has given you a new appreciation for the extraordinary complexity of the human body, for the remarkable science that has been done to understand it, and for the men and women who have offered themselves as both explorers and research subjects in the greatest adventure our species has ever undertaken. As always on Deep Space Intelligence, we encourage you to take what you have heard today as a starting point for your own research, to read the primary literature, to follow the work of the scientists and institutions we have discussed, and to form your own carefully considered views. The science of space medicine is advancing rapidly, and what we know today is a foundation, not a ceiling. There is much more to explore. There always is. Thank you for spending this time with us. This is Deep Space Intelligence, and this has been Liam. Until next time. But before we close, there are several dimensions of this story that deserve more careful attention. Dimensions that often get overlooked in the headlines about puffy faces and shrinking bones, because they speak to something deeper about the nature of human biology and the future we are trying to build. Let us talk about what space reveals about the body's relationship with time. Everything we have discussed, the bone dissolution, the cardiovascular remodeling, the mitochondrial disruption, the telomere changes, the brain fluid reorganization, can be understood in a broader context as a kind of accelerated biological aging. Not aging in every sense of the word and not irreversibly, but aging in the sense of accumulated biological stress, in the sense of systems that have been pushed beyond their optimal operating range for an extended period and bear the marks of that stress at a cellular and molecular level. The comparison between spaceflight-induced white matter changes and the normal changes of aging, where the spaceflight changes were found to exceed what is typically observed over the same period on Earth, is one of the most arresting findings in the neuroimaging literature precisely because of this implication. Space medicine researchers sometimes describe the challenge as one of biological time compression. A year in space may impose physiological burdens on the body that would, under normal Earth conditions, accumulate over many more years of ordinary life. The body then has to undo that compression when it returns, recovering in a year or two what took the spaceflight environment months to impose. That this recovery is largely possible for most systems and for current mission durations is remarkable. That it is not complete, or not guaranteed, for every system in every individual is the frontier that current research is working to understand and manage. The telomere story, with its counterintuitive elongation during the mission and subsequent rapid shortening on return, fits into this framework in an interesting way. The initial elongation has been interpreted by some researchers as a possible mobilization of stem cells with longer telomeres released into the circulation as a kind of biological emergency response to the stresses of spaceflight. The body, in other words, may be drawing on deep reserves of biological youth, activating pools of younger cells to help manage the demands of the environment. If that interpretation is correct, it is a form of biological borrowing, using future capacity to meet present demands. The rapid shortening after landing, leaving a greater proportion of short telomeres than were present before the mission, would then represent the payback of that biological debt. This interpretation remains speculative. The research community has not reached consensus on the mechanism behind the telomere dynamics observed in the twin study, and subsequent research is still working to replicate and extend those findings in larger cohorts. But it frames the overall biological picture of spaceflight in a way that is both scientifically interesting and humanly significant. The body does not simply suffer passively under the stresses of space. It actively mobilizes, adapts, borrows, compensates, and reorganizes. It treats the spaceflight environment as a challenge to be survived and managed, deploying every physiological tool in its considerable arsenal, and most of the time, for current mission durations, it succeeds. The immune system's behaviour in space deserves a closer look in this context. We mentioned earlier that the immune system goes into a kind of hyperactivation state in the early phases of spaceflight, with elevated inflammatory markers and an altered gene expression pattern that one researcher described as being almost on high alert. But the picture of immune function in space is considerably more nuanced than simple activation or suppression. Different arms of the immune system respond differently to the spaceflight environment. Studies have found alterations in the balance between different types of immune cells. The ratio of regulatory T cells to effector T cells can shift. Natural killer cell function has been found to be impaired in some studies. B cell populations and their antibody-producing capacity show changes. The production of certain cytokines is elevated while others are suppressed. What this adds up to is not simply a weaker or stronger immune system, but a differently configured one, a system that has been reorganized by the combination of microgravity, radiation, altered sleep, psychological stress, and changed microbiome that the spaceflight environment collectively represents. The clinical significance of this reconfiguration is still being mapped. The documented reactivation of latent herpes viruses is one sign that the reorganized immune system is not keeping the same surveillance capabilities as before. The finding that certain vaccine responses in space appear to be maintained suggests that the adaptive immune system, the part that generates specific antibodies against specific pathogens, retains significant functionality. The true operational impact on an astronaut's ability to fight off infections or manage inflammatory conditions during a long-duration mission remains an area of active concern and investigation. There is also the question of how the microbiome, the vast internal ecosystem of microorganisms that we carry within us and that influences our health in ways researchers are still discovering, fares in the spaceflight environment. We know from the twin study and other research that the gut microbial community shifts during spaceflight, with changes in the diversity and relative proportions of bacterial species. The specific functional consequences of these microbial changes are not yet fully understood. On Earth, the gut microbiome is now known to play roles not only in digestion, but in immune regulation, metabolic health, mental well-being through the gut-brain axis, and even in cognitive function through pathways involving the production of neuroactive compounds. A microbiome that has been disrupted by months of weightlessness, altered diet, disrupted circadian rhythms, elevated radiation, and psychological stress is potentially a microbiome that is performing all of those functions somewhat differently than it would on Earth. This is an area where space medicine research and Earth-based microbiome science are beginning to converge in productive ways. The closed, tightly monitored environment of the space station provides a kind of natural experiment in microbiome dynamics that is very difficult to replicate in ordinary life on Earth, where the variables affecting microbial communities are essentially impossible to control. Data from astronaut microbiome studies is informing the broader understanding of how extreme environmental stress affects the gut microbial ecosystem, with potential implications for patients undergoing intensive medical treatments, people in extreme occupational environments, and the elderly facing the disruption of their own microbial communities through illness and hospitalization. The skin changes we touched on earlier are worth revisiting in more detail, because they speak to a broader principle about how the entire body surface responds to the removal of gravitational mechanical stimulation. The skin is not merely a passive covering. It is a dynamic, multi-layered tissue that responds to mechanical loading, to ultraviolet light, to temperature, to microbial contact, and to a host of hormonal and immune signals. On Earth, the skin of the feet and lower legs is subjected to constant mechanical pressure and friction from standing and walking. The skin of the back and buttocks bears compressive loading from sitting and lying. These loading patterns maintain the thickness and structural organization of the skin in these regions through mechanotransduction, the process by which physical forces are converted into biochemical signals that regulate cellular behavior. In weightlessness, the loading patterns change profoundly and uniformly. The feet are no longer subjected to the pressure of standing. The back no longer bears the load of reclining against a surface. The entire body floats in a perpetual state of near unloading. The mechanotransductive signals that maintain the skin structure diminish across the entire body surface. Within weeks, reports from astronauts consistently describe skin that has become thinner, more sensitive, and more easily irritated than before the mission. The soles of the feet, which on Earth develop a tough calloused structure adapted to the repeated mechanical challenge of walking, become soft and tender in orbit, the calluses dissolving as they are no longer needed, replaced by skin that is almost uncomfortably sensitive to contact when it encounters surfaces after landing. This thinning and sensitization of the skin has real practical implications. Wound healing, which requires the migration and proliferation of skin cells across a defect and the formation of new blood vessels to supply the rebuilding tissue, is impaired in the microgravity environment. Animal studies have found delayed wound healing in space, and astronaut reports are consistent with this finding. In the context of a long-duration mission, where a crew member might sustain an injury during a spacewalk or in the course of maintenance work, impaired wound healing is a genuine operational concern. The combination of immunological changes, vascular remodeling, and reduced skin integrity creates a physiological substrate that heals more slowly and less reliably than the same person would have healed before the mission. These are the kinds of considerations that drive the development of onboard medical capabilities for future deep space missions. The ISS is within communications range of Earth, with a time delay of only fractions of a second. Medical consultations with ground-based physicians are essentially real-time. A medical emergency on the station can be managed with ground support, and if necessary, the crew can return to Earth within a matter of hours to a day. A crew on the way to Mars, or on the Martian surface, would be facing light-speed communication delays of between 3 and 22 minutes in each direction, depending on orbital positions, making real-time consultation impossible and requiring a level of medical autonomy that current astronaut training programs are beginning to address but have not yet fully solved. Surgical capabilities in microgravity present unique challenges. Drug stability over the multi-year timescales of a Mars mission is an active area of pharmaceutical research. The medical system for a Mars crew would need to be, in a very real sense, a small hospital capable of managing emergencies ranging from acute illness to traumatic injury, without the option of calling for help. This medical autonomy challenge extends to psychological health, which we have touched on but which deserves its own direct consideration. The psychological stresses of long-duration deep space travel go well beyond the garden-variety workplace stress of life on the International Space Station. The ISS crew can look out the window and see the Earth, large and bright and present, a constant visual reminder of home and humanity. A crew transiting through deep space to Mars would see the Earth shrink to a point of light indistinguishable from the stars within weeks of departure. The loss of that visual connection to home is not trivial. Research on analog environments, including Antarctic research stations and submarine deployments, documents the psychological impact of losing contact with the familiar visual landscape of the world. The third quarter effect we mentioned earlier, where morale and motivation tend to dip roughly 3/4 of the way through a long mission, has been documented across multiple analog studies and in some long-duration spaceflight reports. On a mission to Mars, the third quarter would arrive at a point when Earth is far away. Mars is not yet close enough to appear as a disk rather than a dot. The novelty of the voyage has long since faded, and the crew must function at high performance levels while managing the physiological burden of months in microgravity and radiation. The psychological design of that mission, the management of workload and autonomy, and interpersonal dynamics and contact with ground support and meaningful activity will be as critical to mission success as any piece of hardware or countermeasure protocol. NASA's Human Research Program has identified behavioral health and performance as one of the 5 major human spaceflight hazards for long-duration deep space missions, alongside space radiation, hostile and closed environments, distance from Earth, which affects both communication and medical evacuation, and altered gravity fields. The program is actively funding research into all 5 hazard categories, using a combination of ISS studies, analog environment research, ground-based physiological and psychological studies, and computational modeling to build the evidence base for future mission design. The Artemis missions, which aim to return humans to the lunar surface and eventually establish a sustained lunar presence, represent the first step in this progression, and the physiological data gathered from those missions will be critical. Lunar surface missions involve partial gravity at 1/6 of Earth's, which is meaningfully different from both weightlessness and Earth normal, and which presents physiological questions that current research cannot fully answer, because no human has been on the lunar surface for more than about 3 days since the Apollo program ended in 1972. How bones and muscles respond to long-duration 1/6 gravity exposure is not known from direct measurement. How the vestibular system adapts to lunar gravity after months of transit in weightlessness is not known. Whether the cardiovascular remodeling that occurs in zero gravity partially reverses in 1/6 gravity during transit to the Moon is an open question with significant implications for the physical capacity of lunar surface workers. These are all answerable questions. They will be answered through the work that is being planned right now by the scientists and engineers at NASA, ESA, JAXA, Roscosmos, the Chinese National Space Administration, and the growing constellation of commercial space companies that are increasingly contributing to both the operational and the research dimensions of human spaceflight. The knowledge base that will protect the first humans on Mars is being built today, in laboratory studies and in orbit, one careful measurement at a time. And here is perhaps the most important thing to understand about all of this research, all of this careful, painstaking, sometimes alarming documentation of what space does to the human body. None of it has concluded that humans cannot go. None of it has raised a biological barrier so fundamental that it closes the frontier. Every challenge documented by space medicine research is a challenge that scientists and engineers are actively working to address. Every risk identified is a risk that countermeasure development is working to mitigate. The picture is complex. It is not uniformly reassuring. It involves real costs and real uncertainties. But it is the picture of a challenge that can be managed, that is being managed, and that will be managed better with each successive mission as the science advances. There is a story in the research that does not always come through in the headlines. It is a story about a species that evolved on one world, that discovered another world, and that is now, generation by generation, building the knowledge and the technology and the medical capability to make the journey safely. The physiological adaptation that made it possible for early humans to spread from Africa to every corner of the Earth, adapting to Arctic cold and equatorial heat, and high-altitude oxygen deprivation, and coastal and inland and desert environments, did not require us to be perfectly suited to any of those environments. It required us to be adaptable enough, and smart enough, and organized enough to supplement our biology with tools and knowledge and community support. The tools for space are different in their nature and their complexity, but they serve the same function. The exercise machines on the International Space Station are our answer to gravity's absence. The radiation dosimeters are our response to the invisible particle rain from distant supernovae. The pharmaceutical countermeasures for bone loss are our workaround for the osteoclasts that do not know there is no mechanical reason left to resorb bone. The psychological support programs are our communal response to the isolation that no evolutionary history prepared us for. We are not designed for space. We design solutions to the fact that we are not designed for space. That distinction is everything. The men and women who will eventually land on Mars and look up at a sky that is the colour of butterscotch at sunset, and feel the 1/3 gravity pull of a world that has been waiting, geologically patient, for the 4.5 billion years of its existence to see a living mind look out at it and think, this is another world, and I am standing on it. Those people will carry in their bodies the accumulated biological burden of everything we have discussed today. Their bones will be somewhat thinner than when they launched. Their muscles will have been maintained but not entirely preserved by the best exercise countermeasures science could devise. Their vision may have subtly shifted. Their brains will have adapted and compensated and adapted again. Their genomes will carry the record of months of cosmic ray damage, partially repaired, persistently marked. And they will still be there. They will still be functional, thinking, wondering, working human beings, doing science and engineering and exploration in a way that no unmanned probe, however sophisticated, can replicate. The human presence is not simply a convenience or a tradition. It is a capability. The capability to observe and adapt and respond and discover in real time, to be curious and creative and flexible in ways that our most advanced robots are not. The biological cost of putting that capability beyond the Earth is real. The value of what it can accomplish is, in the long view, potentially beyond calculation. That is the story we have been following today, from the moment of launch to the instant of MECO to the first floating seconds of weightlessness, to the fluid cascade and the vestibular crisis, and the slowly thinning bones and the shifting brain, and the silent work of cosmic rays in the dark. It is the story of a body that was built for one world, asked to survive in another, and doing so with the full complexity and resilience and limitation and wonder that all biological things carry within them. We're grateful you followed it with us. Thank you for being part of Deep Space Intelligence. This has been Liam. Until we meet again. There is one more dimension worth exploring before we truly close, because it sits at the intersection of everything we have covered and points toward the next chapter of the story. It concerns not what space does to the body in isolation, but what the combination of all these changes means for performance on a planetary surface, specifically on Mars, where the mission does not end at landing but only truly begins. Imagine the scenario: 6 to 8 months of transit in zero gravity. Everything we have described has been playing out in the crew's bodies the entire way. Bone loss accumulating at roughly 1% per month, muscles maintained as well as possible by the daily exercise protocol but not perfectly preserved. The cardiovascular system adapted to weightlessness. The vestibular system recalibrated to a world without up and down. The brain fluids redistributed, the ventricles expanded, the white matter subtly reorganized. And then the spacecraft decelerates into the Martian atmosphere, and the crew, for the first time in half a year, experiences gravitational loading again. Not Earth gravity, but Martian gravity, at approximately 38% of Earth normal, somewhere between 0 and 1, a partial gravity environment that the body has no pre-existing adaptation to. What happens in that moment, physiologically? The honest answer is that we do not fully know, because no human being has experienced it. We can model it. We can reason from what we know about the transition from weightlessness to Earth gravity and extrapolate to a lower gravity level. We can use animal studies and bedrest analog data and computational models. But the actual human physiological response to the transition from zero gravity transit to Martian surface gravity is an empirical question that will only be answered when someone makes the trip. What we can say with reasonable confidence is that the crew arriving at Mars will be physiologically compromised relative to their pre-launch baseline in several important respects. Their bones will be weaker. Their muscles will be less powerful, particularly in the lower body and back. Their cardiovascular systems will be adapted to zero gravity and may struggle initially to maintain adequate blood pressure and cerebral perfusion in the new gravitational field. Their vestibular systems will be in transition, adapting from the zero-gravity calibration they have settled into toward whatever stable configuration Martian gravity allows. Their spines, elongated by months of weightlessness, will begin to recompress under the new gravitational load, with all the pain and risk of herniation that we described in the terrestrial context of returning ESS astronauts. This is precisely the moment when the crew needs to perform at their highest level. Landing on Mars, establishing habitat integrity, deploying equipment, and beginning the scientific and operational work of a surface mission requires physical capability, cognitive sharpness, and reliable motor coordination. The physiological state of the crew at the moment of landing is thus one of the central human factors concerns in Mars mission design. Mission architects are working to sequence the landing day and early surface activities to minimize demands on the crew during the most acute phase of gravitational readaptation, building in time for physiological recovery before the most physically demanding tasks are required. This is one of the strongest arguments for the artificial gravity research we discussed earlier. A spacecraft that could provide even partial gravitational loading during transit, keeping the crew's cardiovascular systems, bones, muscles, and vestibular systems more closely aligned with the Martian surface gravity they're heading toward, would arrive at Mars with a crew in significantly better physiological condition than one that transited in full weightlessness. The engineering challenges are real and substantial, but the operational payoff, in terms of crew capability at the most critical moment of the mission, could be decisive. And there is the question of the Martian environment itself, which presents biological challenges beyond everything we have already covered. The Martian atmosphere is approximately 95% carbon dioxide, at a pressure less than 1% of Earth's surface pressure, far too thin and chemically hostile to breathe. The surface temperature averages around minus 60 degrees Celsius, with swings between roughly minus 125 at the poles and near zero at the equator in summer. The regolith, the dust and soil that covers the Martian surface, contains perchlorates, chemically reactive compounds that are toxic to humans at certain exposure levels and that could pose respiratory risks if contaminated dust were tracked into habitat spaces. The lack of a global magnetic field and the thin atmosphere means the Martian surface receives significantly more radiation than the Earth's surface, though somewhat less than deep space because Mars itself provides partial shielding from below. A surface mission would require pressure suits, carefully managed airlock protocols, and a continuous awareness of the radiation dose accumulating in the crew's bodies, day by day, added to everything they already absorbed during the transit. The combination of transit radiation and surface radiation exposure over the duration of a Mars mission is one of the primary factors driving mission planners toward minimizing total mission duration, a constraint in direct tension with the scientific and operational ambitions of a surface mission. More time on the surface means more science, more exploration, more return on the extraordinary investment of getting there. But more time also means more radiation, more bone loss, more muscle atrophy, more physiological degradation. This is the fundamental tension at the heart of human Mars exploration planning. The body needs to come home before the accumulated costs become too high, but the mission needs to stay long enough to be worth the journey. Researchers are exploring pharmacological and genomic approaches to this problem. Studies of natural human variation in radiation sensitivity have identified genetic variants associated with differences in DNA repair capacity, in inflammatory response to radiation damage, and in cancer susceptibility. These findings are being incorporated into crew selection considerations for future deep space missions. The ethical dimensions of genetic screening for mission selection are being actively debated within the space medicine and bioethics communities, a conversation that will only become more relevant as deep space human exploration moves from planning toward reality. The National Academies of Sciences, Engineering and Medicine published a report in the early 2020s examining the potential uses of biotechnology and genetic enhancement for space exploration, noting both the potential benefits in terms of astronaut health and the significant ethical considerations around modifying the human genome for non-therapeutic purposes. What is clear is that the conventional pharmacological and engineering toolkit, though powerful, may not be sufficient for the most ambitious future missions, and that researchers are beginning to look beyond it. As always on this channel, we want to be transparent. Much of this genomic and pharmacological enhancement research is in very early stages, and a healthy scientific skepticism about near-term applicability is warranted. The distance between a promising animal model result and a validated human intervention is vast, and we raise these directions because they are part of the honest conversation happening in the scientific community, not because they represent established solutions. What has been established across 6 decades of human spaceflight and the dedicated work of thousands of researchers in laboratories and medical centers and aboard orbiting spacecraft around the world is an extraordinary body of knowledge about what happens when a human being leaves the planet. We know what the first seconds bring, the G-force of launch, the jarring thunder of ascent, the shocking silence of main engine cutoff. We know what the first hours bring, the cephalad fluid shift, the swelling face, the vestibular confusion, the onset of space motion sickness. We know what the first weeks bring, the spine elongating, the bones beginning their slow dissolution, the muscles adapting down, the cardiovascular system remodeling, the brain moving in its fluid. We know what the months bring, the continued accumulation of radiation damage, the microbiome shifting, the latent viruses reactivating, the immune system running differently, the eyes slowly reshaping, the telomeres doing their counterintuitive dance. And we know what the return brings, the G-forces again, the sudden weight of a body that forgot how heavy it was, the cardiovascular struggle, the weeks of rehabilitation, the slow rebuilding, the vestibular system relearning Earth's gravity, the brain finding its pre-flight organization through months of gradual recovery. We know all of this because people went. They went and they measured, and they came back and they were measured again, and the data accumulated and the knowledge grew, and with it grew the countermeasures and the protocols and the understanding that has made each successive generation of spaceflight safer and more sustainable than the last. The body we have been describing throughout this story, this extraordinary, complicated, resilient, vulnerable, adaptable human body, is not a fixed thing. It is a dynamic process, a continuous negotiation between the organism and its environment, shaped over billions of years by the conditions of one specific world, and now, in the span of a single human lifetime, being asked to negotiate with worlds it has never met. That negotiation is imperfect. The costs are real. But the capacity for negotiation itself, the biological plasticity and the scientific intelligence and the collective will that make spaceflight possible, is one of the most remarkable things about the species that evolved, against all evolutionary expectation, to look at the stars and wonder how to get there. The story of what really happens to the body the moment you enter space is not a story of fragility. It is not a cautionary tale about the limits of human biology. It is a story about the full, complex, sometimes alarming, ultimately astonishing range of what a human body can experience, adapt to, endure, recover from, and carry forward into the unknown. It is a story still very much in progress, written in measurements and scans and blood samples and bone density readings, and the honest testimony of the men and women who have lived inside it. We are grateful you followed it with us from beginning to end. This has been Liam on Deep Space Intelligence. The exploration continues.